The urinary bladder is an incredibly dynamic organ that collects and releases urine throughout a person's life. Urine produced by the kidneys enters the bladder through a pair of ureters and is stored there until it is expelled through the urethra. The bladder is able to expand when filled with urine and to collapse to its original shape when emptied because of the interplay between the bladder's neuromuscular activity and the elastic nature of its wall. The muscle layer, or detrusor, contributes to bladder elasticity. A network of smooth muscle cells and their surrounding extracellular matrix forms the detrusor muscle layer. Smooth muscle cells contain chains of actin and myosin filaments that slide apart or together to expand or contract each cell. This coordinated smooth muscle activity allows the bladder to fill and empty. The extracellular matrix between these cells contains collagen fibers, proteoglycans, and elastic fibers. These structures play a role in smooth muscle cell function as well as bladder expansion and contraction. The bladder experiences excessive stretching or attempts greater contraction when urine output is interrupted. This interruption is usually due to some obstruction at the urethra or bladder outlet. Potential causes of obstruction are numerous. In adults, benign prostatic hyperplasia is the most common cause. In infants, posterior urethral valves are a classic form of obstruction, while in many children, damaged or uncoordinated nerve impulses interfering with the proper relaxation of outlet muscles during urination can block urine flow. When the bladder is blocked, urine inflow outpaces urine outflow. As the bladder fills, isometric pressure is put on the stretched muscle cells. When the bladder wall contracts but the urine cannot be expelled, isotonic pressure builds up in the muscle cells. As collagen fibers and other components in the ECM stretch, they transmit pressure to the smooth muscle cells via their attachment to cell surface integrin proteins. This force is then transmitted to the cytoskeleton within the muscle cells. Thus, each cell recognizes this increased pressure in the environment and sends a cascade of signals to its nucleus. Within the nucleus, in response, many genes, including the genes coding for metalloproteinases, are activated. This leads to overproduction of MMPs, releasing a surge of MMPs into the ECM. These MMPs break down the structures within the ECM, releasing growth factors normally sequestered between the ECM fibers. Through this degradation, the broken fragments of ECM fibers become exposed. These fragments are called neoepitopes. The released growth factors and neoepitopes bind to various receptor proteins on the surface of the smooth muscle cells, triggering a cascade of responses leading to fibrosis. The muscle cells begin to grow and proliferate excessively. The new cells also produce more ECM as well as excess MMPs, which create more growth factors and neoepitopes. As a result of this interaction between the ECM and smooth muscle cells, a vicious cycle of fibroproliferative muscle disease is set in motion. The fibroproliferative muscle mass thickens the bladder wall, reducing the bladder's elasticity and compliance. The bladder will no longer be able to expand during urine collection or collapse when it is emptied, even if the urethral blockage is removed. Ultimately, this cycle can cause kidney damage, incontinence, and infection. Further research into the key components of this process can help us discover new ways to prevent or treat bladder hypertrophy in patients with bladder obstructions.